of spectroscopy, but it's the boring part of spectroscopy. All right. So again, remember this is the two different species that you're looking at, right? Okay. And how do you know it's two different species again? Not the peaks. Yeah, yeah, like, fair enough. That help? You want to try it? Yeah, that's good. Yeah, the isosbestic point. I wish they would have named it something like the inflection point, but you know that has a different meaning. No, honestly, the isosbestic point is kind of difficult to remember. It's also kind of a pain in the ass to say. Like, it's not, you have to slow down to do it. Anyways, that tells you if it's two species, right? If it has one of those points, then it's almost certainly two species, okay? It also limits if it's two species, that also limits your math, right? Because whatever you have for x, the px here has to be different, doesn't it? See that? So the px and x are always the total amounts of x. And so that really helps you out. The increments of p are going to be added to a fixed quantity of x, and the absorption of x at 450 nanometers will decrease right there, while the px will increase at the absorption of 545 nanometers. Note in this case, you actually have a bit of a contribution at that wavelength from x. Did you see that? So these bands are close enough that they're not going to resolve individually. Okay? So the absorbance at this point is actually a mixture of both these. And the absorbance at this point is a mixture of both these things.
So just to clarify, all the different lines on there, are those different measurements taken?
Yes. So what you're looking at is a titration. So you start off with pure x, no p, right? And then you would add p, so you're adding p. And your x goes down and is converted to px. And that goes up. Okay? Does that make sense?
Yeah. And the more like bound together they are, closer is px.
Okay, so the stronger the binding, then yes, it will be closer and closer to just following the addition of p here as being just this increase right here. But it really doesn't matter. This still works even if you have poor binding, strong binding, whatever. Okay? Because it's just going to be a titration. You'll still get an equivalence point at some point. Yeah, not all of it won't be in the form of px, but that's okay. You can still tell the equivalence point. It's one of the reasons we are doing things like scratchard plots and all that stuff, right? Is because it doesn't depend on finding an endpoint, does it? Yeah. And yeah, that's one of those big reasons, right? It's just a much, much better way. Like, finding the endpoint would be like the entry level of analytical chemistry, right? It works for a lot of things, and it's an easy thing to do. But we don't really do finding the endpoint much anymore, do we? No, we do things like adding set amounts and then monitoring that relationship, right? Okay. And so you can do things like monitoring the absorptions. You can use the, remember the equations we set up with the multiple Beer's laws? And then solve for the concentrations. Yeah, you can do things like that if you're trying to figure out concentration. Yeah, that's probably the most common industrially. Yeah, it's not common academically and research-wise. Well, like you're not going to do that as a research project. If you find the concentration of something or the amount of something, you probably were like synthesizing something, or you're doing. Remember the article we looked at that looked at the reactants that are left over in different medicines, something like that. It's not really to find the concentration though, right? It's coupled with something else. Yeah. Yeah, but you can do things like publish and do publications and get paid to do research to find like equilibrium constants of various different important drugs. You can look at binding studies. Yeah, there's a lot more stuff you can do. You can tell if this is a new protein or the same protein, or what sort of effects ion has on binding by doing one of these studies, because you can find the binding constants, right? Yeah. So I'm giving you a bunch of tools that you can use to look at the universe, and really your imagination is the limits of those tools. Okay?
That makes sense.
Yeah. Yeah, I don't want you to think of these as like set experiments that you would have to do. And even the experiments we do are not really set experiments that you would have to do it exactly that way. If you understand how the technique works, it's a tool in your toolbox. And then the only thing you're limited by on building that house of experiments, right, would be, am I mixing analogies enough? Would be your imagination and your understanding of your tools, right?
Yeah.
Yeah. Does that make sense?
Yeah, that makes a lot more sense. So I was trying to think like how exactly is that graph like kind of useful, and like in what terms would you kind of use it next?
Yeah, this is literally a titration. And one of the important things about doing a graph like this is that, first off, it gives you two different bands you're monitoring. And so you can do the various different plots that we talked about at the beginning of the chapter. But also, this tells you that there's only two species if you do this, which is very important because there could not be, right? And you have to account for your damn species. Like almost everything we do, you have to account for your damn species somehow, right? If you don't know there's another species, then you're going to be screwed. By the way, this entire thing that I've been talking about, like protein binding and shit, this all works for conformations too. Like this is just how you do conformations as well. You do them in infrared usually, or Raman, but because they're lower energy, you don't usually see a huge difference in energy on like visible light. But yeah, conformations, this also works. Like this could be conformation 1, conformation 2, in say a noble gas, liquid noble gas experiment that you're doing in infrared. Like what I have 20 publications in. Okay? So, there's these are broad application spectroscopy techniques. And you just need to understand the spectroscopy you're using to be able to do these. So it really is powerful. This, along with the first few chapters we did, like those statistics and analytical techniques, those overall broad application things, and then the electrochemistry stuff, you could very easily make a very good career. If you pursue research, you'd be very good at that. If you pursue money, you'd be very good at that. It's hard to pursue both, by the way, which is why I pursued the research. Probably should have pursued the money. But I made great strides in the research. Yeah. Oh well. Okay, so anyways, the protein P without X, again, has no visible absorption. And that's why we don't do this in terms of P. That's why we're titrating in terms of P. See that? Rather than titrating in terms of X. Okay? Actually, typically, titrating with P is typically kind of a bad thing to do. especially if you're using big things like proteins, it's best usually to titrate with the smaller thing, the smaller molecule, okay? And let the big molecule lay. And the reason for that is because it takes a while, if you have something very heavy, for it to get dispersed in solution and actually get into its positions it should be for the absorptions. And yeah, you get you have to wait longer. If you titrate with something very small, it'll disperse in solution very quickly at room temperature, right? But you certainly can't titrate with a thing you can't see. That's not going to work well, right? Yeah. So you got to titrate with the thing you can't see if you can't see one of them. Okay? Does that make sense? Okay, good. Spectroscopy is something I really need another person here because I know far too much and I need to.
When you're saying that, it's like we wouldn't have, like, for our lab that we're doing right now, we wouldn't have had clear EDTA and poured the other stuff into it.
Yeah, it would cause you huge problems, right? Because if it changed color right away, you wouldn't have enough indicator in it. Yeah. So you got to have the color thing.
To be able to tell when it changed.
Exactly. So you can't titrate with the color change, the color thing. Okay. So we can calculate, of course, the extinction coefficient for X here. And again, remember that every time you calculate an extinction coefficient, it's always for a wavelength, right? Because they correspond to how well something absorbs at that wavelength. So we can calculate it for any point on here, but the 2 points that matter are going to be the 545 nanometers right here, and then this as well. This is the one we absolutely need in this case, because the titration is looking at the binding, right? This would just be interesting. Like, there are things you could use this for to help you determine the other, okay? As we saw in the beginning of the chapter, right? But you don't need it. Okay. So note here, this absorption here. There's an absorption right here, isn't there? So a portion of this absorption here is always going to be the species of X, which is why this says Px plus X, right? Because these are adding together, Px and X, to give you this peak height, okay? Note that your X concentration is actually going down. So this peak height is going down like this. And the Px then is building up off of it. So if you just assume this was Px, you'd always get a number slightly lower, right? Because some of that contribution is actually X. And X is changing. Does that make sense? Okay, so you got, this is one of the reasons I was talking about that these bands are not fully resolved. And that's pretty common, very common in UV vis, okay? Almost always going to happen in UV vis. It is less common in things like infrared, microwave. You can resolve them better because you have better resolutions. But still, it's not uncommon. It happens. It happens more than you might want. Okay. So again, that's that black dot that shows you the absorption just from X when we just had X.
That's that first big curve where it's just X, right?
Yeah, this is X right here, but it has an absorption in the 545, which is the one we're looking at. Yeah.
How can you tell it's at 545? Just because the other ones with the PX?
Yeah, so this is kind of an interesting thing. So first off, you have no PX here. So what you would do is you take these ones that are well resolved and you'd find the peak.
So
Yeah.
that's how you can tell for X.
Yeah. And you'll see that the peak actually looks, it almost looks like the peak is shifting, right? But it's actually not. The reason for this is because this is a logarithmic function as it falls off, right? It's a Gaussian function. This falls off faster here. And so it shifts as you get more and more contribution from this peak. It will actually shift the peak over. So when you identify a shoulder, you actually identify it right there. It's something that you have to get used to. Like people all the time will assign the shoulder to this right here. Excuse me. Like up here, the high point. That's not right. That's because of this. Your peak's actually down here, where it shifts over to dropping off really fast. Yeah, because that's your drop off from your peak here, adding to the almost no contribution from this anymore. It's very hard to resolve those, and you would essentially do things like this. You'd either vary the concentrations, or you change temperatures if it's conformation, so that one conformer gets higher, one lower. Or you would do a fit, which doesn't always work well, but where you would model these peaks and then see how they would combine mathematically. It's not as easy as it might sound. Well, it doesn't sound very easy, does it? All right. Anyways, standard path length, hopefully that's like normal now. This is going to be how you find your extinction coefficient. It's just Beer's law, right? Note we can get it from this first pure X spectra. We just take the pure X spectra, find the absorbance at the 545 nanometers. You almost certainly aren't going to do this math only having the pure X spectra though. So one thing I want to point out is you would do this experiment, the entire experiment. You'd identify where your peak is here. And then you'd go back to this spectra of pure X and look at that absorbance. Okay? Because otherwise you may not know where your peak is.
So I guess in this case, not necessarily length, but like one measurement would just be with just X.
Yeah, so these you would typically take a full spectrum. You wouldn't just do it at one wavelength. You do a full spectrum. And so you just do X, you do a full spectrum of it, and you save it. Okay? And then you would do that through your titration. And these ones you'll start being able to resolve your peak. And then you would go back and put your cursor on 545, which is what you find here. And you find the absorbance. You'd plug that absorbance in, find the extinction coefficient. Now you can just mathematically find the concentrations or absorbances, depending on which one you have, every time, right? There you go. And it gives you one of your Beer's law terms, right? To do the two Beer's law terms for each species. Yeah. You know, it takes some steps, but it's not particularly difficult, right? And remember, you're going to know how much of this species is in here because you put it in there. Okay? We do not know the extinction coefficient of px yet, right? We found it for x. Yeah, we've solved some terms. And so now we're going to have to do some estimations and do a solver, right? So we've limited our number of variables to only a few. So we'll have to estimate a k and a extinction coefficient for px, because whenever you do a solver, you always have to start it with an estimate, right? We would then calculate absorbance from Beer's law for a mixture of px and x, which are the two species causing that absorbance, right? That multiple Beer's law, multiple species Beer's law. You know, that's not an official name for it, by the way. Multiple species Beer law, but it should be, right? Yeah. That's what it should be called. Anyways, that's the formula again. It's the same one we've looked at a few times now. You'd plug it into the solver just like we showed before. I'm not going to show that every time because it's a lot of stuff to go through every time, right? But it's the same solver, same Excel spreadsheet. If you made it once, you can copy and paste it and do it again, okay? You don't even have, most of the terms are the same. You'll adjust the values of K and the extinction coefficient of Px until your absorbance calculated at 845 nanometers approaches the absorbance that you observed in each of these experiments.
So for that equation, you're only using the extinction coefficient of Px.
Yeah, this only has the extinction coefficient of Px, but if you have to, you're not going to always know these concentrations exactly.
Yeah.
Remember that this concentration here depends on the K.
Yeah.
Okay?
I was just curious about why it's the same extinction coefficient for X.
Oh, yeah, that's wrong. Yeah, that's wrong.
So that one should just be X, right?
Yeah. You can substitute one into the other, like we did before.
Yeah.
But yeah, this should have been X, because this is just the multi-Beer's law. The other one has the 1 minus. Yeah. Yeah. God, every time. That's another one of those damn pictures from your book, isn't it? Yes, it is. Shit. Oh, I'm gonna have to go through and make all these pictures because they're pictures. I can't just edit them. This shit is just. Your book is so good, but the pictures they provide me are so shitty. And the tables, right? Oh man.
I've seen that a couple times on like I'm doing the homework. I start reading the book. It like contradicts itself. It's like one time it was one of those like 10-point ones.
Mhm.
And like, oh yeah, find like this equation, and one of the pictures it had was literally just the delta sign. And like I was like, it wasn't like delta, it wasn't the change of anything. It was just the delta sign. And I mean like that was the correct one. And I was just like, are you serious?
Yeah, they really need somebody to, like, the book has a good editor, but all the other stuff that they release does not. Whoever's doing the editing for it is really failing. Really badly, right? Ah, man. The homework's new, by the way. They just released online homework for that. Like maybe 2-3 years ago. Yeah, I was pretty excited. That's nice. I used to have to do the book stuff. And then I had no idea what the hell was going on at home. So I never knew anything. Okay, so again, this is going to be that least squares fit. Remember that? Where you minimize the least squares. And so the least squares criteria is going to minimize the sum of the squares, the differences between your observed and your calculated absorbances. That will be that cell I-27. They actually show this in figure 19.8 in case you want to see how exactly you set that up, which is this. Do you need me to go through each of these things, or do you think you guys will be okay? Okay, if you have any difficulties understanding what is what in this, please do let me know. Like, I can go through point by point, I just don't think I don't think you want it. But if you do, let me know, okay?
First, the highlighted box, the E or the extinction coefficient of K,
Mm-hmm.
is that like the first estimate that you put in, or is that one that's based on other values?
You know, I honestly don't remember. That looks like an actual value, though. So my guess would be it's a solved value. Frankly speaking, what you do is you just plug in a value, and then you see if it works. So you hit solve. And if it doesn't work, you're going to see that this is going to come up with something stupid, ridiculous, like a negative value or something, right? And, or a absolutely massive value, 10 to the 100, right? And this right here will not minimize properly. So if this works correctly, this value here should minimize to close to 0, right? And typically what you're going to see is close to 0 is going to be something like 10 to the negative 4, 10 to the negative 5, right? Because remember, you're looking at absorbances. These are 0.1 values. So this should be about 1,000 times or so less than this one. Does that make sense? They should be something on the orders of these, right? Okay. And you can kind of get a sense of this, what would be, because remember, if you change these values in here, you'll have some feed-ins. Okay? So, yeah, there's not really a great way to say, like, this is going to be this value. But again, you kind of have a sense of what it should be. Most of these epsilons were like 1,000 something. So, you know, if it gives you wrong, you'd increase it by a factor of 10 or decrease it by a factor of 10. That make sense? Yeah, there isn't a perfect, like, this will give you a right every time. If you're doing a full-on study of this, what you would want to do is use simplified predictive calculations. Things like, there are a variety of, I'm trying to, like, you guys are several classes away from me to understand those sort of computational chemistry calculations. So even the terminology that would be used is foreign to you guys. Essentially, it's programs that would predict various different constants for a molecule or a binding complex, okay? If you were going to do a full-on study for this would be something you do in like grad school or past grad school. You would do a low-order one that would take very little computational resources, and that would give you a predicted value. You'd run the experiment, and then you'd plug those values in. That makes sense? Okay. Like we did that a lot with Gaussian calculations. You run lower order, you plug those into the Gaussian calculations, so it gives a better minima, because remember, it optimizes to a minima. And then you would take those values and plug them in when you do your actual calculations on derived values from a spectroscopic source, like molecular geometry from microwave data. Okay? And that give you a good starting point. The problem being, if you optimize from something very far away, sometimes you run into local minima, and it never gets to the true minima, the lowest energy one, or the lowest reduction one here, the lowest least squares. Okay, so this is the method of continuous variation. This is also called Jobs method. Let's suppose several complexes can form between species P and X. So P plus X, P in 2X form, and P in 3X form. Okay? So if one complex dominates, the method of continuous variance allows us to determine the stoichiometry of the predominant complex. P and X will be mixed. You'll keep the P and X constant, the concentration's constant, but you'll change the X and P ratio. Okay, so here's some actual data for this, okay? So we have 2.5 millimole solution of P here, and then X right here. These are mixed to give different total px ratios. So here we have the same concentrations for both, right? But then we change the volumes that we're mixing. Typically you change this in a nice round number fashion, okay? Because typically these complexes are going to be whole number complex, okay? If you do geosciences, by the way, that's not necessarily true. There are minerals and stuff that have fractional complex, okay? Because they have, minerals are much more variable. Like you get a formula for a mineral. So you could have 2x on one of the minerals and only 1x on the other, and there'd be another thing that has a similar charge that replaces it. It gives you the same mineral overall. Okay? Anyways, we're not going to go a lot into that. I just wanted you to know that that is a possibility. It's means that you don't have the same composition throughout. This you do. Okay, so basically what we're doing is we're changing the volumes to give us a total of 10 every time, right? And so we go 1 to 9, 1, 2 to 8. You get the idea, right? And you want to try to give it a nice whole number composition. So like 2.5 to 7.5. Why did we do that? Well, that's 3 to 1, isn't it? Okay? And it has the total of the same volume, which is 10, doesn't it? Okay? Okay, so then you would calculate your mole ratios. Because you've kept your concentrations the same between those two, you get a direct just this, the large number, divided by the small number, right? So 9 divided by 1, 9 to 1, right? That's what you do. So just ratio of x to p. Take x, divide by p, right? There you go. Okay. So then this right here would be your mole fraction of x for each of these. So you would take your moles of x, which is right there, and divide it by the moles of x plus the moles of p. And again, you would just get that directly from concentration times volume, right? Note that you can do all these in millimoles if you want. It's fine. Whatever, right? You plug that in, and that gives you your mole fractions of x right here. Okay. So again, make sure you keep your total composition the same every time. Because if you change your total composition, it's going to change your spectrum, right? So the absorbance of each solution would then be measured. So now we have the concentrations worked out. We'll measure the absorbances, okay? The correct absorbance would equal the measured absorbance minus Beer's law for this species, P, and Beer's law for X. So the absorbance of the free P and the free X are subtracted from the measured absorbance, and then this is corrected absorbances will be plotted against these mole fractions of X. There's several ways you can do this part, but the easiest way is literally just to make up solutions of P and X and measure their absorbances. But you can also do the methods we talked about before, which would find these values, right? Okay. Okay, absorbance max is going to be reached at the composition corresponding to the stoichiometry of the predominant complex. The method of continuous variation, and that's the reaction for that method of continuous variation. Again, the absorbance max then is when the mole fraction of X equals the number, which is there, the coefficient, right? Divided by the number again plus 1. So if Px2 dominates, the absorption max occurs at a mole fraction of 2 divided by 2 plus 1, which would be the 0.667 solution right here. See that? Because that would maximize your signal from your product, right? Is that making sense? All the other ones will not have a maximum signal from that product, right? Because they'll be inefficient ratios. Is that clear? Makes sense? Everybody feels good? Fantastic. Okay. Note here, this is the corrected absorbance in this plot. And this is your mole fractions here. Okay? And again, the mole fractions are each of these different deals right there, right? Okay. Okay, Very good. So there's a few precautions. One, you'd have to verify that the complex follows Beer's law. Okay? Remember, there are some caveats to Beer's law, right? You have to have a low concentration. You have to be within the linear region of your response in your spectrometer. So all those caveats that we talked about for Beer's law has to be followed, okay? If your complex does not follow Beer's law, obviously this method would not work at all, right? Because it's going to be based off of Beer's law. So use the constant ionic strength and pH if applicable. This is best done if you can do this in some sort of buffer solution, okay? Note that you should have a constant ionic strength and pH. Of course, this does assume that ionic strength or pH would change, right? You have two neutral, like a neutral protein and a neutral binding agent. That's not going to change ionic strength, okay? If they happen to be neutral as well, then your, pH won't change as well. So it's not like pH and ionic strength always change due to the species you're putting in. 3, you would take readings at more than one wavelength. The maximum should occur at the same mole fraction for each wavelength. 4, do experiments at different total concentrations of P plus X. If a second set of solutions were prepared, the maximum should still occur at the same mole fraction. So if you were to do this experiment, you'd want to do it once, like so, right? And then you'd want to do it with maybe twice this concentration, so 5 and 5 here, and see how that works out, okay? Or you can reduce the concentrations. Depending on what your absorbances were, you'd want to stay in that nice linear range, right? Preferably 0.4 to 0.9. And you wouldn't want to go up to the 1.5 absorbance, right? That'd be problematic. Okay. Again, these are some more examples of this continuous variation method. The naming makes a lot of sense, doesn't it? Continuous variation, literally you continuously vary your ratio. So a titration is more sensible to do this usually. It's a fairly easy way to do this. Titration of EDTA, for example, with copper 2+, we get these figures. The mole fraction of copper 2+ would equal the moles of copper 2+ divided by moles of copper 2+ plus moles of EDTA. And then these would vary, and that would change your mole fractions, okay? As you add that copper 2+ to the EDTA, right? So the maximum absorbance would occur at 0.5. This indicates the formation of a 1-to-1 complex right here. So here's your mole fraction. So yeah, maximum absorbance here is 0.5, right? Which would indicate a 1-to-1. Okay. And everybody's clear why 0.5 is 1-to-1, right? 0.5 is a 1-to-1 complex because this matches this then. That's half. And then this is the same number. Is that? Okay. Okay. All right. So this right here is that clear? So you're literally doing a titration of EDTA with copper, right? And so as you add more copper, your mole fraction of copper increases. And then you'll hit absorbance max. And then you'll start going back down. And usually you want to go ahead and go far enough that you can tell, oh yeah, that was the max, okay? But, you could cut off somewhere here maybe. You can go all the way if you want. It won't matter. You can actually set this up to do it automatically, by the way, if you're clever with instrumentation and computers. So in flow injection analysis, a liquid sample is going to be injected into a continuously flowing liquid carrier. This will contain a reagent that reacts with the sample. As sample flows from the injector to the detector, the sample zone will broaden and react with the reagent. Remember, this is like a stream, right? So if you inject it in one point, it'll bloom, broaden as it goes down until it starts reacting with the whole thing, right? Okay. Where did I leave off? So which would form product, obviously, over your entire solution as it broadens, to which the detector would then respond. There are advantages over batch processes. So remember, this will be a continuous flow. Batch processes would be where you make batches, right? And that's what you've always done before, because this is not, technically we could set this up, but you'd have to leave it set up and you'd have to test the system and get it working first. It would not be something that you could tear down and set up all the time and you'd have any success with.
This is more of like a industrial.
Typically, this is used on industrial scale or for fixed instruments. So you make it and then you put a box around it and it'd be an instrument. Okay? And you do it same every time. This is not something that's going to work well if you set it up and tear it down repeatedly, like a traditional lab experiment, right? This would be more like you could set it up as on a, I've seen these set up before, and I've actually went to a school that had stuff like this. And essentially we had like walls. So there's several different setups. There's custom setups that would essentially be like pegboard walls. And then we'd have like clamps holding the thing against the wall. And then there'd be walls in a bunch of different labs that had those. Okay. And you have to test them and get them calibrated and get them working. Kind of like distillations. Distillation, when you just set it up, always ends up just awful. And then, you grease a few joints, find out where your leaks are, get things positioned correctly, and then it works great. Yeah. Same similar thing here, right? Okay. So some of these advantages over this batch process would include speed. You can automate how the solution handling is done. So you can literally have it come off automatically from like a Coca-Cola mixing tank and then go into one of these, or a drug mixing tank, or whatever. Or you can even do a flow reaction and have it automatically coming off doing this. So on industrial scale, this works really good.
So do you think they would more likely use this or the when you were saying the infrared, or not infrared, but the UV?
I mean, you can do both. Yeah. Oh yeah. The that infrared setup I was talking about, like one of the setups is ramen. They use ramen for bottles. If you have like glass bottles, it works really well. But remember how you were asking about plastic and I said they vary it? This is how. It's one of the ways. So if you're like using plastic, you can test, instead of testing at the bottle stage, you can test at the injector stage. So there's a little thing that goes on the bottle and then sprays the stuff into it. You can test at that. So the line going in, you can test. Anyways, it's a little bit different because technically this would be more for a reaction, but very similar concept. There's the automation, of course. The more automated a process is, the less chances people have to screw it up, right? And that's actually really important because this feels like a long time ago, but do you guys remember where we talked about you have to set up procedures for labs? And you have to put in procedures where you're going to test if you're screwing up, and it was like chapter 2? Yeah. Long time ago, right? But the more automation you have, the easier those procedures are to keep. Like if you have a fully manual lab working on industrial scale, those things can be 100-page long manuals on just procedures that you have to follow for the lab, things you have to do every day, things that, and people get lazy, screw up, especially if management does a bad job, which typically they're pressured to do, right? Like most workplaces are gonna essentially run on a razor-thin margin on number of people, right? And usually pay them as little as they possibly can. So there's a very big incentive not to do those things. Automation fixes a lot of that. You can never be fully automated. It You always have to have a human in the mix because automation can also just screw up and it'll never know it screwed up. But this can also be low cost. It takes a lot less samples because you can measure the whole full deal usually rather than having to take a batch out all the time, right? And remember, you have to take fairly large batches. If you take too small of batches, all your measurements are going to be inaccurate, right? Anyways, so it's very normal for a flow injection to handle something like 100 samples an hour, which is a lot, right? You know now, 100 samples an hour would be a hell of a lot. You guys are handling what, maybe one sample every 10 minutes for batch sampling? Yeah, that's about the speed of your titration, right? So imagine that, right? 3 samples an hour, 100 samples an hour. Well, I guess it'd be 6 samples an hour right now to 100 samples an hour. 20 times faster, huh? Okay. This is a picture of this, by the way. So this would be your carrier flow. This is then a peristatic pump. That is the same sort of pump that you'd find in like a dialysis machines, that sort of thing. Blood collection, serum collection instruments. They look very, very similar. You would then have the injection valve here. This would be a mixing coil. This allows it to spread and mix. They are typically not straight lines because straight lines would mix very poorly and have very little area to do it, right? And so this is very often a coil like you would see on a, the pigtail coils. This would then be your flow cell right here. Notice it's sort of a resting forward motion to some degree. So you would have light in. This is your flow cell, giving you a larger volume to pass the light through. This would be a very fixed distance right here. This entire thing would then be your flow cell. Where it comes in, you have the fixed distance, which light passes through, and then it leaves. Okay? This part right here would be a fiber optic that would collect your signal. Okay? This could be UV vis, this could be Raman, this could be many things. Okay? The fiber optic setup that you'd have here would vary depending, but like UV vis absorption would just be direct light going through, then fiber optic carrying it off. You know a fiber optic, right? Wire that carries light. Okay. It's literally just like a very specific technique to stretch like plastic, and by wrapping it, it redirects light along the pathway, so then you can have a bent pathway, right? And it will carry most of the light, vast majority. Actually, good fiber optics are very good at that. Oh, sorry, okay. And then that goes to the detector. We'll pick up here next time and go on to this part. Okay, you all have a great day, and holy shit, I went really slow today, didn't I?